This unit provided an introduction to business data analytics from several perspectives. As data analytics are used in many fields other than business, so you discovered that some topics in this unit covered data analytics topics without specific applications in business. But the majority of the applications were in support of business decision-making. This unit began with an overview of the current state of business data analytics. Next, we looked at the various steps in the data-driven decision cycle that support business decision-making. The unit concluded with a survey of common business data analytics applications, advanced applications, and a brief overview of various ethical considerations in how we collect and use data. A familiar adage in data analysis is garbage in, garbage out, meaning that no matter how good the analysis tool is, and no matter how good the analyst is, without good data, we cannot produce good data analysis. This topic explores some of the tools and techniques for obtaining data relevant to the business decision at hand and cleaning the data by removing entry errors, duplications, handling missing data, and dealing with extreme data observations that are not relevant to the analysis question, sometimes called outliers. We begin the unit with an overview of data sources and some of the common database systems we might encounter that store business data and support big data applications. Next, we introduce various sampling and data collection methodologies and tools for business data generation. Then we explore tools and techniques for data cleaning and preparation. The unit concludes with an overview of data storage and management with a brief introduction into data analytics for advanced applications in machine learning. The collection and storage of modern business data involves a variety of data sources feeding data into database storage systems often hosted in cloud-based database platforms. This topic begins with an introduction to data collection and storage for data analytics using the Google Cloud Platform, GCP. Next, we look at an overview of the modern business data analytics pipeline and the collection of systems that work together to collect, store, analyze, and report. The topic concludes with a summary of the data analysis pipeline tools available from Amazon Web Services, AWS. What is data analytics? Data analytics converts raw data into actionable insights. It includes a range of tools, technologies, and processes used to find trends and solve problems using data. Data analytics can shape business processes, improve decision-making, and foster business growth. Why is data analytics important? Data analytics helps companies gain more visibility and a deeper understanding of their processes and services. It gives them detailed insights into the customer experience and customer problems. By shifting the paradigm beyond data to connect insights with action, companies can create personalized customer experiences, build related digital products, optimize operations, and increase employee productivity. What is big data analytics? Big data describes large sets of diverse data, structured, unstructured, and semi-structured, that are continuously generated at high speed and in high volumes. Big data is typically measured in terabytes or petabytes. 1 petabyte is equal to 1 million gigabytes. To put this in perspective, consider that a single HD movie contains around 4 gigabytes of data. 1 petabyte is the equivalent of 250,000 films. Large datasets measure anywhere from hundreds to thousands to millions of petabytes. Big data analytics is the process of finding patterns, trends, and relationships in massive datasets. These complex analytics require specific tools and technologies, computational power, and data storage that support the scale. How does big data analytics work? Big data analytics follows 5 steps to analyze any large datasets. Data collection, data storage, data processing, data cleansing, data analysis, data collection. This includes identifying data sources and collecting data from them. Data collection follows ETL or ELT processes. ETL, extract, transform, load. In ETL, the data generated is first transformed into a standard format and then loaded into storage. ELT, Extract Load Transform. In ELT, the data is first loaded into the storage and then transformed into the required format. Data storage. Based on the complexity of data, it can be moved to storage such as cloud data warehouses or data lakes. Business intelligence tools can access it when needed. Data lakes versus data warehouses. A data warehouse is a database optimized to analyze relational data coming from transactional systems and business applications. The data structure and schema are defined in advance to optimize for fast searching and reporting. Data is cleaned, enriched, and transformed to act as the single source of truth that users can trust. Data examples include customer profiles and product information. A data lake is different because it can store both structured and unstructured data without any further processing. The structure of the data or schema is not defined when data is captured. This means you can store all of your data without careful design, which is particularly useful when the future use of the data is unknown. Data examples include social media content, IoT device data, and non-relational data from mobile apps. Organizations typically require both data lakes and data warehouses for data analytics. AWS Lake Formation and Amazon Redshift can take care of your data storage needs. Data processing. When data is in place, it has to be converted and organized to obtain accurate results from analytical queries. Different data processing options exist to do this. The choice of approach depends on the computational and analytical resources available for data processing. Centralized processing. All processing happens on a dedicated central server that hosts all the data. Distributed processing. Data is distributed and stored on different servers. Batch processing. Pieces of data accumulate over time and are processed in batches. Real-time processing. Data is processed continuously, with computational tasks finishing in seconds. Data cleansing. Data cleansing involves scrubbing for any errors, duplications, inconsistencies, redundancies, wrong formats, etc. It's also used to filter out any unwanted data for analytics. Data analysis. This is the step in which raw data is converted to actionable insights. There are 4 types of data analytics. 1. Descriptive analytics. Data scientists analyze data to understand what happened or what is happening in the data environment. It is characterized by data visualization such as pie charts, bar charts, line graphs, tables, or generated narratives. 2. Diagnostic analytics. Diagnostic analytics is a deep dive or detailed data analytics process to understand why something happened. It is characterized by techniques such as drill down, data discovery, data mining, and correlations. In each of these techniques, multiple data operations and transformations are used for analyzing raw data. 3. Predictive analytics. Predictive analytics uses historical data to make accurate forecasts about future trends. It is characterized by techniques such as machine learning, forecasting, pattern matching, and predictive modeling. In each of these techniques, computers are trained to reverse engineer causality connections in the data. 4. Prescriptive analytics. Prescriptive analytics takes predictive data to the next level. It not only predicts what is likely to happen, but also suggests an optimum response to that outcome. It can analyze the potential implications of different choices and recommend the best course of action. It is characterized by graph analysis, simulation, complex event processing, neural networks, and recommendation engines. What are the different data analytics techniques? Many computing techniques are used in data analytics. Let's take a look at some of the most common ones. Natural language processing. Natural language processing is the technology used to make computers understand and respond to spoken and written human language. Data analysts use this technique to process data like dictated notes, voice commands, and chat messages. Text mining. Data analysts use text mining to identify trends in text data like emails, tweets, researches, and blog posts. It can be used for sorting news content, customer feedback, and client emails. Sensor data analysis. Sensor data analysis is the examination of the data generated by different sensors. It is used for predictive machine maintenance, shipment tracking, and other business processes where machines generate data. Outlier analysis. Outlier analysis or anomaly detection identifies data points and events that deviate from the rest of the data. Can data analytics be automated? Yes, data analysts can automate and optimize processes. Automated data analytics is the practice of using computer systems to perform analytical tasks with little or no human intervention. These mechanisms vary in complexity. They range from simple scripts or lines of code to data analytics tools that perform data modeling, feature discovery, and statistical analysis. For example, a cybersecurity firm might use automation to gather data from large swathes of web activity, conduct further analysis, and then use data visualization to showcase results and support business decisions. Can data analytics be outsourced? Yes, companies can bring in outside help to analyze data. Outsourcing data analytics allows the management and executive team to focus on other core operations of the business. Dedicated business analytics teams are experts in their field. They know the latest data analytics techniques and are experts in data management. This means they can perform data analysis more efficiently, identify patterns, and successfully predict future trends. However, knowledge transfer and data confidentiality could present business challenges in outsourcing. How is data analytics used in business? Businesses capture statistics, quantitative data, and information from multiple customer-facing and internal channels. But finding key insights takes careful analysis of a staggering amount of data. This is no small feat. Let's look at some examples of how data analytics and data science can add value to a business. Data analytics improves customer insight. Data analytics can be conducted on datasets from various customer data sources like third-party customer surveys, customer purchase logs, social media activity, computer cookies, website or application statistics. Analytics can reveal hidden information like customer preferences, popular pages on a website, the length of time customers spend browsing, customer feedback, and interaction with website forms. This enables businesses to respond efficiently to customer needs and increase customer satisfaction. Case study: How Nextdoor used data analytics to improve customer experience. Nextdoor is the neighborhood hub for trusted connections and the exchange of helpful information, goods, and services. Using the power of the local community, Nextdoor helps people lead happier and more meaningful lives. Nextdoor used Amazon Analytics solutions to measure customer engagement and the efficacy of their recommendations. Data analytics enabled them to help customers build better connections and view more relevant content in real time. Data analytics informs effective marketing campaigns. Data analytics eliminates guesswork from marketing, product development, content creation, and customer service. It allows companies to roll out targeted content and fine-tune it by analyzing real-time data. Data analytics also provides valuable insights into how marketing campaigns are performing. Targeting, message, and creatives can all be tweaked based on real-time analysis. Analytics can optimize marketing for more conversions and less ad waste. Case study: How Zynga used data analytics to enhance marketing campaigns. Zynga is one of the world's most successful mobile game companies, with hit games including Words with Friends, Zynga Poker, and Farmville. These games have been installed by more than 1 billion players worldwide. Zynga's revenue comes from in-app purchases, so they analyze real-time in-game player action using Amazon Kinesis to plan more effective in-game marketing campaigns. Data analytics increases operational efficiency. Data analytics can help companies streamline their processes, reduce losses, and increase revenue. Predictive maintenance schedules, optimized staff rosters, and efficient supply chain management can exponentially improve business performance. Case study: how BT Group used data analytics to streamline operations. BT Group is the UK's leading telecommunications and network serving customers in 180 countries. BT Group's network support team used Amazon Kinesis data analytics to obtain a real-time view of calls made across the UK on their network. Network support engineers and fault analysts use the system to spot, react, and successfully resolve problems in the network. The collection and storage of modern business data involves a variety of data sources feeding data into database storage systems often hosted in cloud-based database platforms. This topic began with an introduction to data collection and storage for data analytics using the Google Cloud Platform, GCP. Next, we looked at an overview of the modern business data analytics pipeline and the collection of systems that work together to collect, store, analyze, and report. The topic concluded with a summary of the data analysis pipeline tools available from Amazon Web Services, AWS. This topic begins with an introduction to data types and sampling methodologies for collecting business data. Next, we complete a brief video overview of qualitative and quantitative data and the objectives and tools for descriptive and inferential statistics. Finally, the topic presents an introduction to data collection methods, types, and tools. You're probably asking yourself the question, when and where will I use statistics? If you read any newspaper, watch television, or use the internet, you will see statistical information. There are statistics about crime, sports, education, politics, and real estate. Typically, when you read a newspaper article or watch a television news program, you are given sample information. With this information, you may make a decision about the correctness of a statement, claim, or fact. Statistical methods can help you make the best educated guess. Since you will undoubtedly be given statistical information at some point in your life, you need to know some techniques for analyzing the information thoughtfully. Think about buying a house or managing a budget. Think about your chosen profession. The fields of economics, business, psychology, education, biology, law, computer science, police science, and early childhood development require at least one course in statistics. Included in this chapter are the basic ideas and words of probability and statistics. You will soon understand that statistics and probability work together. You will also learn how data are gathered and what good data can be distinguished from bad. The science of statistics deals with the collection, analysis, interpretation, and presentation of data. We see and use data in our everyday lives. In this course, you will learn how to organize and summarize data. Organizing and summarizing data is called descriptive statistics. Two ways to summarize data are by graphing and by using numbers, for example, finding an average. After you have studied probability and probability distributions, you will use formal methods for drawing conclusions from good data. The formal methods are called inferential statistics. Statistical inference uses probability to determine how confident we can be that our conclusions are correct. Effective interpretation of data, inference, is based on good procedures for producing data and thoughtful examination of the data. You will encounter what will seem to be too many mathematical formulas for interpreting data. The goal of statistics is not to perform numerous calculations using the formulas, but to gain an understanding of your data. The calculations can be done using a calculator or a computer. The understanding must come from you. If you can thoroughly grasp the basics of statistics, you can be more confident in the decisions you make in life. Probability. Probability is a mathematical tool used to study randomness. It deals with the chance, the likelihood of an event occurring. For example, if you toss a fair coin 4 times, the outcomes may not be 2 heads and 2 tails. However, if you toss the same coin 4,000 times, the outcomes will be close to half heads and half tails. The expected theoretical probability of heads in any one toss is 12 or 0.5. Even though the outcomes of a few repetitions are uncertain, there is a regular pattern of outcomes when there are many repetitions. After reading about the English statistician Karl Pearson, who tossed a coin 24,000 times with a result of 12,012 heads, one of the authors tossed a coin 2,000 times. The results were 996 heads. The fraction 996,2000 is equal to 0.498, which is very close to 0.5, the expected probability. The theory of probability began with the study of games of chance such as poker. Predictions take the form of probabilities. To predict the likelihood of an earthquake, of rain, or whether you will get an A in this course, we use probabilities. Doctors use probability to determine the chance of a vaccination causing the disease the vaccination is supposed to prevent. A stockbroker uses probability to determine the rate of return on a client's investments. You might use probability to decide to buy a lottery ticket or not. In your study of statistics, you will use the power of mathematics through probability calculations to analyze and interpret your data. Key terms. In statistics, we generally want to study a population. You can think of a population as a collection of persons, things, or objects under study. To study the population, we select a sample. The idea of sampling is to select a portion or subset of the larger population and study that portion, the sample, to gain information about the population. Data are the result of sampling from a population. Because it takes a lot of time and money to examine an entire population, sampling is a very practical technique. If you wish to compute the overall grade point average at your school, it would make sense to select a sample of students who attend the school. The data collected from the sample would be the students' grade point averages. In presidential elections, opinion poll samples of 1,000 to 2,000 people are taken. The opinion poll is supposed to represent the views of the people in the entire country. Manufacturers of canned carbonated drinks take samples to determine if a 16-ounce can contain 16 ounces of carbonated drink. From the sample data, we can calculate a statistic. A statistic is a number that represents a property of the sample. For example, if we consider one math class to be a sample of the population of all math classes, then the average number of points earned by students in that one math class at the end of the term is an example of a statistic. The statistic is an estimate of a population parameter, in this case the mean. A parameter is a numerical characteristic of the whole population that can be estimated by a statistic. Since we considered all math classes to be the population, then the average number of points earned per student over all the math classes is an example of a parameter. One of the main concerns in the field of statistics is how accurately a statistic estimates a parameter. The accuracy really depends on how well the sample represents the population. The sample must contain the characteristics of the population in order to be a representative sample. We are interested in both the sample statistic and the population parameter in inferential statistics. In a later chapter, we will use the sample statistic to test the validity of the established population parameter. A variable or random variable, usually notated by capital letters such as X and Y, is a characteristic or measurement that can be determined for each member of a population. Variables may be numerical or categorical. Numerical variables take on values with equal units, such as weight in pounds and time in hours. Categorical variables place the person or thing into a category. If we let X equal the number of points earned by one math student at the end of a term, then X is a numerical variable. If we let Y be a person's party affiliation, then some examples of Y include Republican, Democrat, and Independent. Y is a categorical variable. We could do some math with values of X, calculate the average number of points earned, for example, but it makes no sense to do math with values of y. Calculating an average party affiliation makes no sense. Data are the actual values of the variable. They may be numbers or they may be words. Datum is a single value. Two words that come up often in statistics are mean and proportion. If you were to take 3 exams in your math classes and obtain scores of 86, 75, and 92, you would calculate your mean score by adding the 3 exam scores and dividing by 3. Your mean score would be 84.3 to 1 decimal place. If, in your math class, there are 40 students and 22 are men and 18 are women, then the proportion of men students is 2240 and the proportion of women students is 1840. Mean and proportion are discussed in more detail in later chapters. Note: the words mean and average are often used interchangeably. The substitution of one word for the other is common practice. The technical term is arithmetic mean, and average is technically a center location. However, in practice among non-statisticians, average is commonly accepted for arithmetic mean. Data may come from a population or from a sample. Lowercase letters like X or Y generally are used to represent data values. Most data can be put into the following categories: qualitative, quantitative. Qualitative data are the result of categorizing or describing attributes of a population. Qualitative data are also often called categorical data. Hair color, blood type, ethnic group, the car a person drives, and the street a person lives on are examples of qualitative, categorical data. Qualitative, categorical data are generally described by words or letters. For instance, hair color might be black, dark brown, light brown, blonde, gray, or red. Blood type might be AB+, O-, or B+. Researchers often prefer to use quantitative data over qualitative, categorical data because it lends itself more easily to mathematical analysis. For example, it does not make sense to find an average hair color or blood type. Quantitative data are always numbers. Quantitative data are the result of counting or measuring attributes of a population. Amount of money, pulse rate, weight, number of people living in your town, and number of students who take statistics are examples of quantitative data. Quantitative data may be either discrete or continuous. All data that are the result of counting are called quantitative discrete data. These data take on only certain numerical values. If you count the number of phone calls you receive for each day of the week, you might get values such as 0, 1, 2, or 3. Data that are not only made up of counting numbers, but that may include fractions, decimals, or irrational numbers, are called quantitative continuous data. Continuous data are often the results of measurements like lengths, weights, or times. A list of the lengths in minutes for all the phone calls that you make in a week, with numbers like 2.4, 7.5, or 11.0, would be quantitative continuous data. Qualitative data discussion. Below are tables comparing the number of part-time and full-time students at De Anza College and Foothill College enrolled for the most recent spring quarter. The tables display counts, frequencies, and percentages or proportions, relative frequencies. The percent columns make comparing the same categories in the colleges easier. Displaying percentages along with the numbers is often helpful, but it is particularly important when comparing sets of data that do not have the same totals, such as the total enrollments for both colleges in this example. Notice how much larger the percentage for part-time students at Foothill College is compared to De Anza College. Tables are a good way of organizing and displaying data, but graphs can be even more helpful in understanding the data. There are no strict rules concerning which graphs to use. Two graphs that are used to display qualitative, categorical data are pie charts and bar graphs. In a pie chart, categories of data are represented by wedges in a circle and are proportional in size to the percent of individuals in each category. In a bar graph, The length of the bar for each category is proportional to the number or percent of individuals in each category. Bars may be vertical or horizontal. A Pareto chart consists of bars that are sorted into order by category size, largest to smallest. Look at Figure 1.4 and Figure 1.5 and determine which graph, pie or bar, you think displays the comparisons better. It is a good idea to look at a variety of graphs to see which is the most helpful in displaying the data. We might make different choices of what we think is the best graph, depending on the data and the context. Our choice also depends on what we are using the data for. Percentages that add to more or less than 100%. Sometimes percentages add up to be more than 100% or less than 100%. In the graph, the percentages add to more than 100% because students can be in more than one category. A bar graph is appropriate to compare the relative size of the categories. A pie chart cannot be used. It also could not be used if the percentages added to less than 100%. Omitting categories/missing data. The table displays ethnicity of students, but is missing the other/unknown category. This category contains people who did not feel they fit into any of the ethnicity categories or declined to respond. Notice that the frequencies do not add up to the total number of students. In this situation, create a bar graph and not a pie chart. Sampling. Gathering information about an entire population often costs too much or is virtually impossible. Instead, we use a sample of the population. A sample should have the same characteristics as the population it is representing. Most statisticians use various methods of random sampling in an attempt to achieve this goal. This section will describe a few of the most common methods. There are several different methods of random sampling. In each form of random sampling, each member of a population initially has an equal chance of being selected for the sample. Each method has pros and cons. The easiest method to describe is called a simple random sample. Any group of n individuals is equally likely to be chosen as any other group of n individuals if the simple random sampling technique is used. In other words, each sample of the same size has an equal chance of being selected. Besides simple random sampling, there are other forms of sampling that involve a chance process for getting the sample. Other well-known random sampling methods are the stratified sample, the cluster sample, and the systematic sample. To choose a stratified sample, divide the population into groups called strata and then take a proportionate number from each stratum. For example, you could stratify, group, your college population by department, and then choose a proportionate simple random sample from each stratum, each department, to get a stratified random sample. To choose a simple random sample from each department, number each member of the first department, number each member of the second department, and do the same for the remaining departments. Then use simple random sampling to choose proportionate numbers from the first department and do the same for each of the remaining departments. Those numbers picked from the first department, picked from the second department, and so on represent the members who make up the stratified sample. To choose a cluster sample, divide the population into clusters, groups, and then randomly select some of the clusters. All the members from these clusters are in the cluster sample. For example, if you randomly sample 4 departments from your college population, the 4 departments make up the cluster sample. Divide your college faculty by department. The departments are the clusters. Number each department, and then choose 4 different numbers using simple random sampling. All members of the 4 departments with those numbers are the cluster sample. To choose a systematic sample, randomly select a starting point and take every nth piece of data from a listing of the population. For example, suppose you have to do a phone survey. Your phone book contains 20,000 residence listings. You must choose 400 names for the sample. Number the population 1 to 20,000 and then use a simple random sample to pick a number that represents the first name in the sample. Then choose every 50th name thereafter until you have a total of 400 names. You might have to go back to the beginning of your phone list. Systematic sampling is frequently chosen because it is a simple method. A type of sampling that is non-random is convenience sampling. Convenience sampling involves using results that are readily available. For example, a computer software store conducts a marketing study by interviewing potential customers who happen to be in the store browsing through the available software. The results of convenience sampling may be very good in some cases and highly biased, favor certain outcomes in others. Sampling data should be done very carefully. Collecting data carelessly can have devastating results. Surveys mailed to households and then returned may be very biased. They may favor a certain group. It is better for the person conducting the survey to select the sample respondents. True random sampling is done with replacement. That is, once a member is picked, that member goes back into the population and thus may be chosen more than once. However, for practical reasons, in most populations, simple random sampling is done without replacement. Surveys are typically done without replacement. That is, a member of the population may be chosen only once. Most samples are taken from large populations, and the sample tends to be small in comparison to the population. Since this is the case, sampling without replacement is approximately the same as sampling with replacement because the chance of picking the same individual more than once with replacement is very low. Sampling without replacement instead of sampling with replacement becomes a mathematical issue only when the population is small. When you analyze data, it is important to be aware of sampling errors and non-sampling errors. The actual process of sampling causes sampling errors. For example, the sample may not be large enough. Factors not related to the sampling process cause non-sampling errors. A defective counting device can cause a non-sampling error. In reality, a sample will never be exactly representative of the population, so there will always be some sampling error. As a rule, the larger the sample, the smaller the sampling error. In statistics, a sampling bias is created when a sample is collected from a population and some members of the population are not as likely to be chosen as others, remember. Each member of the population should have an equally likely chance of being chosen. When a sampling bias happens, there can be incorrect conclusions drawn about the population that is being studied. Critical evaluation. We need to evaluate the statistical studies we read about critically and analyze them before accepting the results of the studies. Common problems to be aware of include problems with samples. A sample must be representative of the population. A sample that is not representative of the population is biased. Biased samples that are not representative of the population give results that are inaccurate and not valid. Self-selected samples, responses only by people who choose to respond, such as call-in surveys, are often unreliable. Sample size issues. Samples that are too small may be unreliable. Larger samples are better, if possible. In some situations, having small samples is unavoidable and can still be used to draw conclusions. Examples: crash testing cars or medical testing for rare conditions. Undue influence: collecting data or asking questions in a way that influences the response. Non-response or refusal of subject to participate. The collected responses may no longer be representative of the population. Often, people with strong positive or negative opinions may answer surveys, which can affect the results. Causality. A relationship between two variables does not mean that one causes the other to occur. They may be related, correlated, because of their relationship through a different variable. Self-funded or self-interest studies. A study performed by a person or organization in order to support their claim. Is the study impartial? Read the study carefully to evaluate the work. Do not automatically assume that the study is good, but do not automatically assume the study is bad either. Evaluate it on its merits and the work done. Misleading use of data, improperly displayed graphs, incomplete data, or lack of context. Confounding, when the effects of multiple factors on a response cannot be separated. Confounding makes it difficult or impossible to draw valid conclusions about the effect of each factor. Once you have a set of data, you will need to organize it so that you can analyze how frequently each datum occurs in the set. However, when calculating the frequency, you may need to round your answers so that they are as precise as possible. Levels of measurement. The way a set of data is measured is called its level of measurement. Correct statistical procedures depend on a researcher being familiar with levels of measurement. Not every statistical operation can be used with every set of data. Data can be classified into 4 levels of measurement. They are from lowest to highest level: nominal scale level, ordinal scale level, interval scale level, ratio scale level. Data that is measured using a nominal scale is qualitative, categorical. Categories, colors, names, labels, and favorite foods along with yes or no responses are examples of nominal level data. Nominal scale data are not ordered. For example, trying to classify people according to their favorite food does not make any sense. Putting pizza first and sushi second is not meaningful. Smartphone companies are another example of nominal scale data. The data are the names of the companies that make smartphones, but there is no agreed upon order of these brands, even though people may have personal preferences. Nominal scale data cannot be used in calculations. Data that is measured using an ordinal scale is similar to nominal scale data, but there is a big difference. The ordinal scale data can be ordered. An example of ordinal scale data is a list of the top 5 national parks in the United States. The top 5 national parks in the United States can be ranked from 1 to 5, but we cannot measure differences between the data. Another example of using the ordinal scale is a cruise survey where the responses to questions about the cruise are excellent, good, satisfactory, and unsatisfactory. These responses are ordered from the most desired response to the least desired. But the differences between 2 pieces of data cannot be measured. Like the nominal scale data, ordinal scale data cannot be used in calculations. Data that is measured using the interval scale is similar to ordinal level data because it has a definite ordering, but there is a difference between data. The differences between interval scale data can be measured, though the data does not have a starting point. Temperature scales like Celsius, C, and Fahrenheit, F, are measured by using the interval scale. In both temperature measurements, 40 degrees is equal to 100 degrees minus 60 degrees. Differences make sense. But 0 degrees does not because, in both scales, 0 is not the absolute lowest temperature. Temperatures like minus 10 degrees Fahrenheit and minus 15 degrees Celsius exist and are colder than 0. Interval level data can be used in calculations, but one type of comparison cannot be done. 80 degrees Celsius is not 4 times as hot as 20 degrees Celsius, nor is 80 degrees Fahrenheit 4 times as hot as 20 degrees Fahrenheit. There is no meaning to the ratio of 80 to 20 or 4 to 1. Data that is measured using the ratio scale takes care of the ratio problem and gives you the most information. Ratio scale data is like interval scale data, but it has a 0 point and ratios can be calculated. For example, for multiple choice statistics, final exam scores are 80, 68, 20, and 92 out of a possible 100 points. The exams are machine graded. The data can be put in order from lowest to highest, 20, 68, 80, 92. The differences between the data have meaning. The score 92 is more than the score 68 by 24 points. Ratios can be calculated. The smallest score is 0. So 80 is 4 times 20. The score of 80 is 4 times better than the score of 20. A frequency is the number of times a value of the data occurs. According to Table 1.7, there are 3 students who work 2 hours, 5 students who work 3 hours, and so on. The sum of the values in the frequency column, 20, represents the total number of students included in the sample. A relative frequency is the ratio, fraction, or proportion of the number of times a value of the data occurs in the set of all outcomes to the total number of outcomes. To find the relative frequencies, divide each frequency by the total number of students in the sample, in this case, 20. Relative frequencies can be written as fractions, percents, or decimals. Cumulative relative frequency is the accumulation of the previous relative frequencies. To find the cumulative relative frequencies, add all the previous relative frequencies to the relative frequency for the current row, as shown in Table 1.9. In this sample, there are 5 players whose heights fall within the interval 59.95 to 61.95 inches, 3 players whose heights fall within the interval 61.95 to 63.95 inches, 15 players whose heights fall within the interval 63.95 to 65.95 inches, 40 players whose heights fall within the interval 65.95 to 67.95 inches, 17 players whose heights fall within the interval 67.95 to 69.95 inches, 12 players whose heights fall within the interval 69.95 to 71.95, 7 players whose heights fall within the interval 71.95 to 73.95, and 1 player whose heights fall within the interval 73.95 to 75.95. All heights fall between the endpoints of an interval and not at the endpoints. Does aspirin reduce the risk of heart attacks? Is one brand of fertilizer more effective at growing roses than another? Is fatigue as dangerous to a driver as the influence of alcohol? Questions like these are answered using randomized experiments. In this module, you will learn important aspects of experimental design. Proper study design ensures the production of reliable, accurate data. The purpose of an experiment is to investigate the relationship between 2 variables. When one variable causes change in another, we call the first variable the independent variable or explanatory variable. The affected variable is called the dependent variable or response variable. Stimulus, response. In a randomized experiment, the researcher manipulates values of the explanatory variable and measures the resulting changes in the response variable. The different values of the explanatory variable are called treatments. An experimental unit is a single object or individual to be measured. You want to investigate the effectiveness of vitamin E in preventing disease. You recruit a group of subjects and ask them if they regularly take vitamin E. You notice that the subjects who take vitamin E exhibit better health on average than those who do not. Does this prove that vitamin E is effective in disease prevention? It does not. There are many differences between the 2 groups compared in addition to vitamin E consumption. People who take vitamin E regularly often take other steps to improve their health: exercise, diet, other vitamin supplements, choosing not to smoke. Any one of these factors could be influencing health. As described, this study does not prove that vitamin E is the key to disease prevention. Additional variables that can cloud a study are called lurking variables. In order to prove that the explanatory variable is causing a change in the response variable, it is necessary to isolate the explanatory variable. The researcher must design her experiment in such a way that there is only one difference between groups being compared: the planned treatments. This is accomplished by the random assignment of experimental units to treatment groups. When subjects are assigned treatments randomly, all of the potential lurking variables are spread equally among the groups. At this point, the only difference between groups is the one imposed by the researcher. Different outcomes measured in the response variable, therefore, must be a direct result of the different treatments. In this way, an experiment can prove a cause and effect connection between the explanatory and response variables. The power of suggestion can have an important influence on the outcome of an experiment. Studies have shown that the expectation of the study participant can be as important as the actual medication. In one study of performance-enhancing drugs, researchers noted, Results showed that believing one had taken the substance resulted in performance times almost as fast as those associated with consuming the drug itself. In contrast, taking the drug without knowledge yielded no significant performance increment. McClung, M., Collins, D., Because I Know It Will, Placebo Effects of an Ergogenic Aid on Athletic Performance. Journal of Sport and Exercise Psychology. 2007 June 29, 3382-94. Webb, April 30, 2013. When participation in a study prompts a physical response from a participant, it is difficult to isolate the effects of the explanatory variable. To counter the power of suggestion, researchers set aside one treatment group as a control group. This group is given a placebo treatment, an active treatment that cannot directly influence the response variable. The control group helps researchers balance the effects of being in an experiment with the effects of the active treatments. Of course, if you are participating in a study and you know that you are receiving a pill which contains no actual medication, then the power of suggestion is no longer a factor. Blinding or masking in a randomized experiment preserves the power of suggestion. When a person involved in a research study is blinded, they don't know who is receiving the active treatments and who is receiving the placebo treatment. A double-blind experiment is one in which both the subjects and the researchers involved with the subjects are blinded. Average. Also called mean or arithmetic mean, a number that describes the central tendency of the data. Blinding. Not telling participants which treatment a subject is receiving. Categorical variable. Variables that take on values that are names or labels. Cluster sampling. A method for selecting a random sample and dividing the population into groups, clusters. Use simple random sampling to select a set of clusters. Every individual in the chosen clusters is included in the sample. Control group. A group in a randomized experiment that receives an inactive treatment but is otherwise managed exactly as the other groups. Convenience sampling. A non-random method of selecting a sample. This method selects individuals that are easily accessible and may result in biased data. Cumulative relative frequency. The term applies to an ordered set of observations from smallest to largest. The cumulative relative frequency is the sum of the relative frequencies for all values that are less than or equal to the given value. Data. A set of observations, a set of possible outcomes. Most data can be put into two groups, qualitative, an attribute whose value is indicated by a label, or quantitative, an attribute whose value is indicated by a number. Quantitative data can be separated into two subgroups, discrete and continuous. Data is discrete if it is the result of counting, such as the number of students of a given ethnic group in a class or the number of books on a shelf. Data is continuous if it is the result of measuring, such as distance traveled or weight of luggage. Double-blind experiment. An experiment in which both the subjects of an experiment and the researchers who work with the subjects are blinded. Experimental unit. Any individual or object to be measured. Explanatory variable. The independent variable in an experiment, the value controlled by researchers. Frequency. The number of times a value of the data occurs. Lurking variable. A variable that has an effect on a study even though it is neither an explanatory variable nor a response variable. Mathematical models. A description of a phenomenon using mathematical concepts such as equations, inequalities, distributions, etc. Non-sampling error. An issue that affects the reliability of sampling data other than natural variation. It includes a variety of human errors including poor study design, biased sampling methods, inaccurate information provided by study participants, data entry errors, and poor analysis. Numerical variable. Variables that take on values that are indicated by numbers. Parameter. A number that is used to represent a population characteristic and that generally cannot be determined easily. Placebo. An inactive treatment that cannot directly affect the response variable, used to counter the power of suggestion. Population. All individuals, objects, or measurements whose properties are being studied. Probability. A number between 0 and 1 inclusive that gives the likelihood that a specific event will occur. Proportion. The number of successes divided by the total number in the sample. Qualitative data. A set of observations, a set of possible outcomes. Qualitative data has an attribute whose value is indicated by a label. Quantitative data. A set of observations, a set of possible outcomes. Quantitative, an attribute whose value is indicated by a number. Data can be separated into two subgroups, discrete and continuous. Data is discrete if it is the result of counting, such as the number of students of a given ethnic group in a class or the number of books on a shelf. Data is continuous if it is the result of measuring, such as distance traveled or weight of luggage. Random assignment. The act of organizing experimental units into treatment groups using random methods. Random sampling. A method of selecting a sample that gives every member of the population an equal chance of being selected. Relative frequency. The ratio of the number of times a value of the data occurs in the set of all outcomes to the total number of outcomes. Representative sample. A subset of the population that has the same characteristics as the population. Response variable. The dependent variable in an experiment. The value that is measured for change at the end of an experiment. Sample. A subset of the population studied. Sampling bias. Not all members of the population are equally likely to be selected. Sampling error. The natural variation that results from selecting a sample to represent a larger population. This variation decreases as the sample size increases, so selecting larger samples reduces sampling error. Sampling with replacement. Once a member of the population is selected for inclusion in a sample, that member is returned to the population for the selection of the next individual. Sampling without replacement. A member of the population may be chosen for inclusion in a sample only once. If chosen, the member is not returned to the population before the next selection. Simple random sampling. A straightforward method for selecting a random sample. Give each member of the population a number. Use a random number generator to select a set of labels. These randomly selected labels identify the members of your sample. Statistic. A numerical characteristic of the sample. A statistic estimates the corresponding population parameter. Stratified sampling. A method for selecting a random sample used to ensure that subgroups of the population are represented adequately. Divide the population into groups, strata. Use simple random sampling to identify a proportionate number of individuals from each stratum. Survey. A study in which data is collected as reported by individuals. Systematic sampling. A method for selecting a random sample. List the members of the population. Use simple random sampling to select a starting point in the population. Let K equals number of individuals in the population / number of individuals needed in the sample. Choose every KTH individual in the list starting with the one that was randomly selected. If necessary, return to the beginning of the population list to complete your sample. Treatments. Different values or components of the explanatory variable applied in an experiment. Variable. A characteristic of interest for each person or object in a population. What is data collection? Methods, types, tools. The process of gathering and analyzing accurate data from various sources to find answers to research problems, trends and probabilities, etc., to evaluate possible outcomes is known as data collection. Knowledge is power, information is knowledge, and data is information in digitized form, at least as defined in IT. Hence, data is power. But before you can leverage that data into a successful strategy for your organization or business, you need to gather it. That's your first step. So, to help you get the process started, we shine a spotlight on data collection. What exactly is it? Believe it or not, it's more than just doing a Google search. Furthermore, what are the different types of data collection? And what kinds of data collection tools and data collection techniques exist? If you want to get up to speed about what is data collection process, you've come to the right place. Let's start. What is data collection? Data collection is the process of collecting and evaluating information or data from multiple sources to find answers to research problems, answer questions, evaluate outcomes, and forecast trends and probabilities. It is an essential phase in all types of research, analysis, and decision-making, including that done in the social sciences, business, and healthcare. During data collection, researchers must identify the data types, the sources of data, and the methods being used. We will soon see that there are many different data collection methods. Data collection is heavily reliant on in research, commercial, and government fields. Before an analyst begins collecting data, they must answer 3 questions first. What's the goal or purpose of this research? What kinds of data are they planning on gathering? What methods and procedures will be used to collect, store, and process the information? Additionally, we can divide data into qualitative and quantitative types. Qualitative data covers descriptions such as color, size, quality, and appearance. Unsurprisingly, quantitative data deals with numbers such as statistics, poll numbers, percentages, etc. Unlock new career opportunities today by mastering the art of data management with Simplilearn's comprehensive data management courses. Why do we need data collection? Before a judge makes a ruling in a court case or a general creates a plan of attack, they must have as many relevant facts as possible. The best courses of action come from informed decisions, and information and data are synonymous. The concept of data collection isn't new, as we'll see later, but the world has changed. There is far more data available today, and it exists in forms that were unheard of a century ago. The data collection process has had to change and grow, keeping pace with technology. Whether you're in academia, trying to conduct research, or part of the commercial sector, thinking of how to promote a new product, you need data collection to help you make better choices. Now that you know what data collection is and why we need it, let's look at the different methods of data collection. Data collection could mean a telephone survey, a mail-in comment card, or even some guy with a clipboard asking passersby some questions. But let's see if we can sort the different data collection methods into a semblance of organized categories. Become a data science and business analytics professional. 28% annual job growth by 2026. 11.5 M expected new jobs for data science by 2026. Data scientist. Industry-recognized Data Scientist Master's Certificate from Simplilearn. Dedicated live sessions by faculty of industry experts. 11 months. View program. Professional Certificate in Data Science and Generative AI. Program Completion Certificate from Purdue University Online and Simplilearn. Access to Purdue's Alumni Association membership on program completion. 6 months. View program. Here's what learners are saying regarding our programs. A. Anthony Davis. Simplilearn United States has one of the best programs available online to earn real-world skills that are in demand worldwide. I just completed the Machine Learning Advanced course, and the LMS was excellent. Magdalena Zarafin. Manager Group Accounting and Data Analytics, Chemicals. My decision to upskill myself in data science from Simplilearn was a great choice. After completing my course, I was assigned many new projects to work on in my desired field of data analytics. Not sure what you're looking for? View all related programs. What are the different data collection methods? Primary and secondary methods of data collection are two approaches used to gather information for research or analysis purposes. Let's explore each data collection method in detail. 1. Primary data collection. The first techniques of data collection is primary data collection, which involves the collection of original data directly from the source or through direct interaction with the respondents. This method allows researchers to obtain first-hand information tailored to their research objectives. There are various techniques for primary data collection, including A. Surveys and questionnaires. Researchers design structured questionnaires or surveys to collect data from individuals or groups. These can be conducted through face-to-face interviews, telephone calls, mail, or online platforms. B. Interviews. Interviews involve direct interaction between the researcher and the respondent. They can be conducted in person, over the phone, or through video conferencing. Interviews can be structured, with predefined questions, semi-structured, allowing flexibility, or unstructured, more conversational. C. Observations. Researchers observe and record behaviors, actions, or events in their natural setting. This method is useful for gathering data on human behavior, interactions, or phenomena without direct intervention. D. Experiments. Experimental studies involve manipulating variables to observe their impact on the outcome. Researchers control the conditions and collect data to conclude cause and effect relationships. E. Focus groups. Focus groups bring together a small group of individuals who discuss specific topics in a moderated setting. This method helps in understanding the opinions, perceptions, and experiences shared by the participants. 2. Secondary data collection. The next techniques of data collection is secondary data collection, which involves using existing data collected by someone else for a purpose different from the original intent. Researchers analyze and interpret this data to extract relevant information. Secondary data can be obtained from various sources, including A. Published sources. Researchers refer to books, academic journals, magazines, newspapers, government reports, and other published materials that contain relevant data. B. Online databases. Numerous online databases provide access to a wide range of secondary data, such as research articles, statistical information, economic data, and social surveys. C. Government and institutional records. Government agencies, research institutions, and organizations often maintain databases or records that can be used for research purposes. D. Publicly available data. Data shared by individuals, organizations, or communities on public platforms, websites, or social media can be accessed and utilized for research. E. Past research studies. Previous research studies and their findings can serve as valuable secondary data sources. Researchers can review and analyze the data to gain insights or build upon existing knowledge. Data collection tools. Now that we've explained the various techniques, let's narrow our focus even further by looking at some specific tools. For example, we mentioned interviews as a technique, but we can further break that down into different interview types or tools. Word association. The researcher gives the respondent a set of words and asks them what comes to mind when they hear each word. Sentence completion. Researchers use sentence completion to understand the respondent's ideas. This tool involves giving an incomplete sentence and seeing how the interviewee finishes it. Role-playing. Respondents are presented with an imaginary situation and asked how they would act or react if it were real. In-person surveys. The researcher asks questions in person. Online/web surveys. These surveys are easy to accomplish, but some users may be unwilling to answer truthfully, if at all. Mobile surveys. These surveys take advantage of the increasing proliferation of mobile technology. Mobile collection surveys rely on mobile devices like tablets or smartphones to conduct surveys via SMS or mobile apps. Phone surveys. No researcher can call thousands of people at once, so they need a third party to handle the chore. However, many people have call screening and won't answer. Observation. Sometimes, the simplest method is the best. Researchers who make direct observations collect data quickly and easily, with little intrusion or third-party bias. Naturally, this method is only effective in small-scale situations. The importance of ensuring accurate and appropriate data collection. Accurate data collecting is crucial to preserving the integrity of research, regardless of the subject of study or preferred method for defining data, quantitative, qualitative. Errors are less likely to occur when the right data gathering tools are used, whether they are brand new ones, updated versions of them, or already available. Among the effects of data collection done incorrectly include the following: erroneous conclusions that squander resources, decisions that compromise public policy, incapacity to correctly respond to research inquiries, bringing harm to participants who are humans or animals, deceiving other researchers into pursuing futile research avenues, the study's inability to be replicated and validated. When these study findings are used to support recommendations for public policy, there is the potential to result in disproportionate harm, even if the degree of influence from flawed data collecting may vary by discipline and the type of investigation. Let us now look at the various issues that we might face while maintaining the integrity of data collection. Issues related to maintaining the integrity of data collection. To assist the error detection process in the data gathering process, whether they were done purposefully, deliberate falsifications, or not, maintaining data integrity is the main justification, systematic or random errors. Quality assurance and quality control are two strategies that help protect data integrity and guarantee the scientific validity of study results. Each strategy is used at various stages of the research timeline. Quality control, tasks that are performed both after and during data collecting. Quality assurance, events that happen before data gathering starts. Let us explore each of them in more detail now. Quality assurance. As data collecting comes before quality assurance, its primary goal is prevention, i.e., forestalling problems with data collection. The best way to protect the accuracy of data collection is through prevention. The uniformity of protocol created in the Thorough and Exhaustive Procedures Manual for Data Collecting serves as the best example of this proactive step. The likelihood of failing to spot issues and mistakes early in the research attempt increases when guides are written poorly. There are several ways to show these shortcomings. Failure to determine the precise subjects and methods for retraining or training staff employees in data collecting. List of goods to be collected, in part. There isn't a system in place to track modifications to processes that may occur as the investigation continues. Instead of detailed, step-by-step instructions on how to deliver tests, there is a vague description of the data gathering tools that will be employed. Uncertainty regarding the date, procedure, and identity of the person or people in charge of examining the data. Incomprehensible guidelines for using, adjusting, and calibrating the data collection equipment. Now, let us look at how to ensure quality control. Quality control. Despite the fact that quality control actions, detection/monitoring and intervention, take place both after and during data collection, the specifics should be meticulously detailed in the procedures manual. Establishing monitoring systems requires a specific communication structure, which is a prerequisite. Following the discovery of data collection problems, there should be no ambiguity regarding the information flow between the primary investigators and staff personnel. A poorly designed communication system promotes slack oversight and reduces opportunities for error detection. Direct staff observation conference calls during site visits or frequent or routine assessments of data reports to spot discrepancies, excessive numbers, or invalid codes can all be used as forms of detection or monitoring. Site visits might not be appropriate for all disciplines. Still, without routine auditing of records, whether qualitative or quantitative, it will be challenging for investigators to confirm that data gathering is taking place in accordance with the manual's defined methods. Additionally, quality control determines the appropriate solutions, or actions, to fix flawed data gathering procedures and reduce recurrences. Problems with data collection, for instance, that call for immediate action include fraud or misbehavior, systematic mistakes, procedure violations, individual data items with errors, issues with certain staff members or a site's performance. Researchers are trained to include one or more secondary measures that can be used to verify the quality of information being obtained from the human subject in the social and behavioral sciences where primary data collection entails using human subjects. For instance, a researcher conducting a survey would be interested in learning more about the prevalence of risky behaviors among young adults, as well as the social factors that influence these risky behaviors' propensity for and frequency. Let us now explore the common challenges with regard to data collection. Become a data science and business analytics professional. 28% annual job growth by 2026. 11.5 M expected new jobs for data science by 2026. Data scientist. Industry-recognized data scientist master's certificate from Simpliliarn. Dedicated live sessions by faculty of industry experts. 11 months. View program. Professional certificate in data science and generative AI. Program completion certificate from Purdue University Online and Simpliliarn. Access to Purdue's Alumni Association membership on program completion. 6 months. View program. Here's what learners are saying regarding our programs. A. Anthony Davis. Simpliliarn United States has one of the best programs available online to earn real-world skills that are in demand worldwide. I just completed the Machine Learning Advanced course, and the LMS was excellent. Magdalena Zarafin. Manager Group Accounting and Data Analytics, Chemicals. My decision to upskill myself in data science from Simpliliarn was a great choice. After completing my course, I was assigned many new projects to work on in my desired field of data analytics. Not sure what you're looking for? View all related programs. What happens after data collection? Once you've gathered your data through various methods of data collection, here is what happens next. Process and analyze your data. At this stage, you'll use various methods to explore your data more thoroughly. This can involve statistical methods to uncover patterns or qualitative techniques to understand the broader context. The goal is to turn raw data into actionable insights that can guide decisions and strategies moving forward. Interpret and report your results. After analyzing the data collected through methods of data collection and research, the next step is to interpret and present your findings. The format and detail depend on your audience. Researchers might require academic papers, M&E teams need comprehensive reports, and field teams often rely on real-time feedback. What's key here is ensuring that the data is communicated clearly, allowing everyone to make informed decisions. Safely store and handle data. Once your data has been analyzed, proper storage is essential. Cloud storage is a reliable option, offering both security and accessibility. Regular backups are also important, as is limiting access to ensure that only the right people are handling sensitive information. This helps maintain the integrity and safety of your data throughout the project. What are common challenges in data collection? Some prevalent challenges are faced while collecting data. Let us explore a few of them to better understand them and avoid them. Data quality issues. The main threat to the broad and successful application of machine learning is poor data quality. Data quality must be your top priority if you want to make technologies like machine learning work for you. Let's talk about some of the most prevalent data quality problems in this blog article and how to fix them. Inconsistent data. When working with various data sources, it's conceivable that the same information will have discrepancies between sources. The differences could be in formats, units, or occasionally spellings. The introduction of inconsistent data might also occur during firm mergers or relocations. Inconsistencies in data tend to accumulate and reduce the value of data if they are not continually resolved. Organizations that focus heavily on data consistency do so because they only want reliable data to support their analytics. Data downtime. Data is the driving force behind the decisions and operations of data-driven businesses. However, there may be brief periods when their data is unreliable or not prepared. Customer complaints and subpar analytical outcomes are only two ways this data unavailability can significantly impact businesses. A data engineer spends significant amount of their time updating, maintaining, and guaranteeing the integrity of the data pipeline. To ask the next business question, there is a high marginal cost due to the lengthy operational lead time from data capture to insight. Schema modifications and migration problems are just two examples of the causes of data downtime. Due to their size and complexity, data pipelines can be difficult to manage. Data downtime must be continuously monitored and reduced through automation. Ambiguous data. Even with thorough oversight, some errors can still occur in massive databases or data lakes. The issue becomes more overwhelming when data streams at a fast speed. Spelling mistakes can go unnoticed, formatting difficulties can occur, and column heads might be deceptive. This unclear data might cause several problems for reporting and analytics. Duplicate data. Streaming data, local databases, and cloud data lakes are just a few of the data sources that modern enterprises must contend with. They might also have application and system silos. These sources are likely to duplicate and overlap each other quite a bit. For instance, duplicate contact information has a substantial impact on customer experience. Marketing campaigns suffer if certain prospects are ignored while others are engaged repeatedly. The likelihood of biased analytical outcomes increases when duplicate data are present. It can also result in ML models with biased training data. Abundance of data. While we emphasize data-driven analytics and its advantages, a data quality problem with excessive data exists. There is a risk of getting lost in abundant data when searching for information pertinent to your analytical efforts. Data scientists, data analysts, and business users devote 80% of their work to finding and organizing the appropriate data. With increased data volume, other problems with data quality become more serious, mainly when dealing with streaming data and significant files or databases. Inaccurate data. Data accuracy is crucial for highly regulated businesses like healthcare. Given the current experience, it is more important than ever to increase the data quality for COVID-19 and later pandemics. Inaccurate information does not provide a true picture of the situation and cannot be used to plan the best course of action. Personalized customer experiences and marketing strategies underperform if your customer data is inaccurate. Data inaccuracies can be attributed to several things, including data degradation, human mistakes, and data drift. Worldwide data decay occurs at a rate of about 3% per month, which is quite concerning. Data integrity can be compromised while transferring between different systems, and data quality might deteriorate with time. Hidden data. The majority of businesses only utilize a portion of their data, with the remainder sometimes being lost in data silos or discarded in data graveyards. For instance, the customer service team might not receive client data from sales, missing an opportunity to build more precise and comprehensive customer profiles. missing out on possibilities to develop novel products, enhance services, and streamline procedures is caused by hidden data. Finding relevant data. Finding relevant data is not so easy. There are several factors that we need to consider while trying to find relevant data, which include relevant domain, relevant demographics. We need to consider relevant time periods and many more factors while trying to find appropriate data. Data irrelevant to our study in any of the factors renders it obsolete, and we cannot effectively proceed with its analysis. This could lead to incomplete research or analysis, recollecting data repeatedly, or shutting down the study. Deciding the data to collect. Determining what data to collect is one of the most important factors while collecting data and should be one of the first factors in collecting data. We must choose the subjects the data will cover, the sources we will use to gather it, and the required information. Our responses to these queries will depend on our aims, or what we expect to achieve utilizing your data. As an illustration, we may choose to gather information on the categories of articles that website visitors between the ages of 20 and 50 most frequently access. We can also decide to compile data on the typical age of all the clients who purchased from your business over the previous month. Not addressing this could lead to double work, the collection of irrelevant data, or the ruin of your study. Dealing with big data. Big data refers to massive data sets with more intricate and diversified structures. These traits typically result in increased challenges while storing, analyzing, and using additional methods of extracting results. Big data refers especially to data sets that are so enormous or intricate that conventional data processing tools are insufficient. The overwhelming amount of data, both unstructured and structured, that a business faces daily. Recent technological advancements have increased the amount of data produced by healthcare applications, the internet, social networking sites, sensor networks, and many other businesses. Low response and other research issues. Poor design and low response rates were shown to be two issues with data collecting, particularly in health surveys that used questionnaires. This might lead to an insufficient or inadequate data supply for the study. Creating an incentivized data collection program might be beneficial in this case to get more responses. Now, let us look at the critical steps in the data collection process. Become a data science and business analytics professional. 28% annual job growth by 2026. 11.5 M expected new jobs for data science by 2026. Data scientist. Industry-recognized data scientist master's certificate from Simpliliarn. Dedicated live sessions by faculty of industry experts. 11 months. View program. Professional certificate in data science and generative AI. Program completion certificate from Purdue University Online and Simpliliarn. Access to Purdue's Alumni Association membership on program completion. 6 months. View program. Here's what learners are saying regarding our programs. A. Anthony Davis. Simpliliarn United States has one of the best programs available online to earn real-world skills that are in demand worldwide. I just completed the Machine Learning Advanced course, and the LMS was excellent. Magdalena Zarafin. Manager Group Accounting and Data Analytics, Chemicals. My decision to upskill myself in data science from Simpliliarn was a great choice. After completing my course, I was assigned many new projects to work on in my desired field of data analytics. Not sure what you're looking for? View all related programs. What are the key steps in the data collection process? In the data collection process, there are 5 key steps. They're explained briefly below. 1. Decide what data you want to gather. The first thing that we need to do is decide what information we want to gather. We must choose the subjects the data will cover, the sources we will use to collect it, and the quantity of information that we will require. For instance, we may choose to gather information on the categories of products that an average e-commerce website visitor between the ages of 30 and 45 most frequently searches for. 2. Establish a deadline for data collection. The process of creating a strategy for data collection can now begin. We should set a deadline for our data collection at the outset of our planning phase. Some forms of data we might want to collect continuously. For instance, we might want to build up a technique for tracking transactional data and website visitor statistics over the long term. However, we will track the data throughout a certain time frame if we are tracking it for a particular campaign. In these situations, we will have a schedule for beginning and finishing gathering data. 3. Select a data collection approach. At this stage, we will select the data collection technique to serve as the foundation of our data gathering plan. We must consider the type of information we wish to gather, the period we will receive it, and the other factors we decide on when choosing the best gathering strategy. 4. Gather information. Once our plan is complete, we can implement our data collection plan and begin gathering data. In our DMP, we can store and arrange our data. We need to be careful to follow our plan and keep an eye on how it's doing. Especially if we are collecting data regularly, setting up a timetable for when we will be checking in on how our data gathering is going may be helpful. As circumstances alter and we learn new details, we might need to amend our plan. 5. Examine the information and apply your findings. It's time to examine our data and arrange our findings after gathering all our information. The analysis stage is essential because it transforms unprocessed data into insightful knowledge that can be applied to better our marketing plans, goods, and business judgments. The analytics tools included in our DMP can assist with this phase. We can put the discoveries to use to enhance our business once we have discovered the patterns and insights in our data. Let us now look at some data collection considerations and best practices that one might follow. Data collection considerations and best practices. We must carefully plan before spending time and money traveling to the field to gather data. While saving time and resources, effective data collection strategies can help us collect richer, more accurate, and richer data. Below, we will be discussing some of the best practices that we can follow for the best results. 1. Take into account the price of each extra data point. Once we have decided on the data we want to gather, we need to consider the expense of doing so. Our surveyors and respondents will incur additional costs for each additional data point or survey question. 2. Plan how to gather each data piece. There is a dearth of freely accessible data. Sometimes the data is there, but we may not have access to it. For instance, unless we have a compelling cause, we cannot openly view another person's medical information. It could be challenging to measure several types of information. Consider how time-consuming and complex it will be to gather each piece of information while deciding what data to acquire. 3. Think about your choices for data collecting using mobile devices. Mobile-based data collecting can be divided into 3 categories. IVRS, Interactive Voice Response Technology, will call the respondents and ask them questions that have already been recorded. SMS data collection will send a text message to the respondent, who can then respond to questions by text on their phone. Field surveyors can directly enter data into an interactive questionnaire while speaking to each respondent, thanks to smartphone apps. We need to select the appropriate tool for our survey and respondents because each has its own disadvantages and advantages. 4. Carefully consider the data you need to gather. It's all too easy to get information about anything and everything, but it's crucial only to gather the information we require. It is helpful to consider these 3 questions. What details will be helpful? What details are available? What specific details do you require? 5. Remember to consider identifiers. Identifiers, or details describing the context and source of a survey response, are just as crucial as the information about the subject or program that we are researching. Adding more identifiers will enable us to pinpoint our program's successes and failures more accurately, but moderation is the key. 6. Data collecting through mobile devices is the way to go. Although collecting data on paper is still common, modern technology relies heavily on mobile devices. They enable us to gather various data types at relatively lower prices and are accurate and quick. With the boom of low-cost Android devices, there aren't many reasons not to choose mobile-based data collecting. Choose the right data science program. Are you thinking about pursuing a career in the field of data science? Simplilearn's data science courses are designed to provide you with the necessary skills and expertise to excel in this rapidly changing field. Here's a detailed comparison for your reference. Conclusion. To sum up, it is vital to master data collection for making decisions that are well-informed and conducting effective research. Once you understand the different data collection techniques and know about the right tools and best practices, you can gather meaningful and accurate data. However, you must address the common challenges and concentrate on the essential steps involved in the process to maintain your data's credibility and achieve good results. We live in the data age, and if you want a career that entirely takes advantage of this, you should consider a career in data science. The Professional Certificate in Data Science and Generative AI will train you in everything you need to know to secure the perfect position. This Data Science PG program is ideal for all working professionals, covering job-critical topics like R, Python programming, machine learning algorithms, NLP concepts, and data visualization with Tableau in great detail. Our interactive learning model provides this with live sessions by global practitioners, practical labs, and industry projects. This topic began with an introduction to data types and sampling methodologies for collecting business data. Next, we completed a brief video overview of qualitative and quantitative data and the objectives and tools for descriptive and inferential statistics. Finally, the topic presented an introduction to data collection methods, types, and tools. This topic delves into more details about various data cleaning techniques, tools, and processes. It begins with another Google Data Analytics certification module explaining methods of data collection, transformation, and storage in support of data analytics projects. Next, we complete a brief tutorial into data cleansing and data preparation methods. The topic concludes with an introduction into data filtering and outlier identification and a demonstration of data cleansing using Python. This topic delved into more details about various data cleaning techniques, tools, and processes. It began with another Google Data Analytics certification module explaining methods of data collection, transformation, and storage in support of data analytics projects. Next, we completed a brief tutorial into data cleansing and data preparation methods. The topic concluded with an introduction into data filtering and outlier identification and a demonstration of data cleansing using Python. This topic explores data storage and management methods and tools, beginning with the next level of data analytics tools and processes using the cloud-based Google Cloud Platform database tools and services. Next, we examine advanced data analytics methods and tools provided by cloud-based tools like Databricks. Finally, we look at the use of mixed methods research and the use of qualitative and quantitative data for business data analytics. Data Management 101 on Databricks. This ebook explains how Databricks streamlines the data management lifecycle in modern organizations. As remote work and distributed systems become more common, data management has become increasingly important. Databricks defines data management as the discipline of collecting, processing, governing, sharing, and analyzing data as a strategic resource in a cost-effective and reliable way. The document begins by outlining the challenges of data management. Many organizations struggle to use their data effectively. According to Forrester, up to 73% of company data goes unused for analytics and decision-making. Data often flows into data lakes for machine learning and into data warehouses for business intelligence. However, data lakes are slow and unreliable for BI, while data warehouses are limited in supporting machine learning. This creates complexity and inefficiency. Databricks addresses these challenges with its Lakehouse platform, which unifies data lakes and data warehouses. Delta Lake, a core component of the platform, adds reliability, performance, and security to data lakes. The Lakehouse architecture supports all phases of the data lifecycle, including ingestion, transformation, analytics, governance, and sharing. For data ingestion, Databricks offers two main solutions. One is a network of partners that integrate with Databricks to move data from various sources into Delta Lake. The other is Autoloader, which efficiently ingests data from cloud storage using structured streaming and schema inference. Once data is ingested, it must be transformed and cleaned. Databricks provides Delta Live Tables, a scalable ETL framework that allows data engineers to build declarative pipelines in SQL or Python. These pipelines adapt to changes in data and include built-in data quality checks. This simplifies operations and ensures reliable data for analytics and machine learning. For analytics, Databricks SQL offers a familiar SQL native experience for data analysts. It allows users to run BI workloads directly on the Lakehouse, create visualizations, and build dashboards. Analysts can connect their preferred BI tools to Databricks SQL endpoints for fast performance and low latency. Data governance is handled through Unity Catalog, which provides fine-grained access control and auditing across the Lakehouse. It supports attribute-based policies and centralizes management of data assets, including tables, models, and dashboards. Unity Catalog works across multiple cloud platforms, enabling secure and scalable governance. Finally, Databricks supports secure data sharing through Delta Sharing, an open protocol that allows organizations to share live data without copying it. Data consumers can access shared data using open source or commercial tools, even if they are not on the same platform. Delta sharing includes privacy and compliance controls for secure access and auditing. In conclusion, Databricks offers a unified platform for managing data from ingestion to analytics. The Lakehouse architecture simplifies data workflows, improves collaboration, and enables organizations to unlock the full value of their data. Mixed methods research, combining qualitative and quantitative data. What is mixed methods research? Mixed methods research is a powerful approach that combines both quantitative and qualitative research methods to gain a more comprehensive understanding of a topic. While quantitative research focuses on numbers and statistical analysis, qualitative research dives into the experiences, opinions, and motivations of people. By combining these two approaches, researchers can explore the what and the why, providing the best of both worlds to deliver richer insights than either method could alone. This approach is particularly valuable when dealing with complex issues that can't be fully understood through numbers or words alone. For instance, you might start with a survey to gather broad data on a population, quantitative, and then follow up with interviews or focus groups to explore deeper meanings and nuances, qualitative. By integrating these findings, you can cross-validate results and gain a more well-rounded understanding of the topic or problem you're exploring. Qualitative versus quantitative research. To understand mixed method studies, it's crucial to first know the differences between qualitative and quantitative research. Quantitative research is all about numbers and measurements. Leveraging tools like surveys, it deals with data that can be counted, categorized, and statistically analyzed. This approach is great for answering questions like how many or what proportion. When you need to measure something precisely, test hypotheses, or identify patterns across large groups. On the other hand, qualitative research is more about exploring depth and meaning. Instead of numbers, it focuses on words, images, and experiences, helping you understand the how and why. Leveraging methods like interviews, focus groups, and open-ended surveys, it's used when you want to dive deep into people's thoughts, feelings, or behaviors. Integrating qualitative and quantitative methods. Crucially, in the context of mixed methods research, these two approaches are not in competition, they're complementary. Integrating both qualitative and quantitative methods isn't just about using both approaches in the same study. It's about strategically combining them in a way that each method enhances and informs the other. There are several ways to integrate these methods, which we'll come on to very soon. But no matter how they're integrated, the goal of mixed methods research is to leverage the strengths of both qualitative and quantitative approaches. When to use mixed methods research. Mixed methods research is a versatile approach that can be applied at various stages of your research process. No matter if your goal is to explore a challenging issue, broaden the scope of your insights, or dig deeper into your data, the aim is to use the right combination of methods throughout your entire research process to make well-rounded, informed decisions. Let's look at the core applications. Throughout your research journey. Mixed methods research isn't just a one-time tool. It's a strategy that can be applied throughout the entire research journey. Imagine you want to understand a new market or consumer behavior. In the beginning, you might rely entirely on qualitative methods, such as interviews or focus groups, to gather deep, rich insights. As your understanding deepens and you begin to form hypotheses, you can then transition to a more quantitative approach. By moving from a qualitative study to a quantitative one, you're not just validating your initial insights, you're also generalizing them, making them actionable on a broader scale. This approach is particularly useful for businesses, especially when research is one of many tasks being juggled. It allows you to adapt your research methods over time, aligning them with the evolving needs of your project and the decisions you need to make. Rather than trying to capture everything in a single study, you can spread your research across multiple phases, using the strengths of each method where they're most needed. Tackling complex research questions. Complex research questions often require a multifaceted approach to capture all the relevant dimensions. Mixed methods research excels here by allowing researchers to tackle complexity head-on, with its dual approach ensuring that no aspect of the research question is overlooked. For instance, you can use qualitative methods to identify the underlying factors of a complex issue, then apply quantitative methods to measure the extent of those factors across a broader population. Generalizing and expanding qualitative findings. Often it's not enough to simply understand a topic on a deep level. You also need to know its breadth and how it may apply to a larger audience. This is again where mixed methods research shines. After gathering in-depth qualitative insights, mixed methods research allows you to use quantitative techniques to test these insights across a broader group, helping you generalize your findings, making them more actionable and relevant to a wider audience. Explaining quantitative results. Mixed methods research allows you to dig deeper into quantitative results by adding a qualitative layer of understanding. Because while numbers can tell you a lot, they don't always give the full story. For instance, if your quantitative data reveals a surprising trend, qualitative methods can help you explore the reasons behind it, helping you explain and contextualize your data. With a mixed methods approach, you can ensure that your quantitative insights aren't just statistically significant, they're also both meaningful and relevant. Benefits of mixed methods research. Mixed methods research brings together the best of both quantitative and qualitative approaches, offering a range of benefits that make it an ideal choice for any researcher or business looking for comprehensive insights. By integrating these methods, you can ensure that your research is not only thorough, but also adaptable to the evolving needs of your projects. Triangulation and validation. One of the standout advantages of mixed methods research is the ability to triangulate and validate your findings. By using both quantitative and qualitative data, you can cross-check your results, ensuring they hold up under different lenses to strengthen the credibility of your conclusions. In practice, having all your data in one place simplifies this validation process. Doing everything within a single platform, like Qualtrics XM for strategy and research, makes it easier to compare and contrast findings, ensuring that your insights are well-rounded and reliable without the need for complex data management. Holistic insights and context. Mixed methods research excels at providing holistic insights. Quantitative data gives you the big picture. Qualitative data fills in the gaps. This combination results in a richer, more nuanced understanding of your research subject. When all your data is accessible and integrated, drawing connections between the broader trends and the detailed stories becomes more straightforward, empowering you to build a more complete and contextually rich narrative to help you make more informed decisions. Flexibility in research design. Mixed methods research is flexible by definition, allowing you to adapt your research design as new questions or challenges arise. Whether you start with a qualitative exploration to define the scope of your research, or you begin with quantitative analysis and follow up with qualitative methods to delve deeper, this flexibility is especially beneficial in fast-paced environments where the ability to pivot quickly can be a huge competitive advantage. A single platform that supports both quantitative and qualitative research enhances this flexibility. With the right tool, you can easily switch between methods, integrate new data, and refine your approach without having to juggle multiple tools or platforms. With a single platform, you're not only saving time, you're also ensuring that your research remains cohesive and aligned with your overall objectives. Types of mixed methods research designs. Mixed methods research isn't a one-size-fits-all approach. There are several designs you can choose from depending on your research goals and the nature of your study. Each design offers a different way to integrate quantitative and qualitative methods, allowing you to tailor your research process to best address specific questions or topics. Let's look at 3 of the most commonly used mixed methods research designs. Convergent parallel design. The convergent parallel design is one of the most straightforward mixed methods approaches. In this design, quantitative and qualitative data are collected simultaneously but analyzed separately. The key is to give both sets of data equal priority, bringing them together during the interpretation phase, before then comparing and contrasting the results to see where they converge or diverge. This design is particularly useful when you want to verify findings and gain a more comprehensive understanding of the topic. For example, you might use quantitative surveys to gather broad data on customer satisfaction while conducting interviews to explore the reasons behind the survey responses. Explanatory sequential design. In the explanatory sequential design, research begins with quantitative data collection and analysis, followed by qualitative methods to explain or build on the quantitative results. This design is especially useful when you have clear quantitative findings that require further exploration to understand their underlying reasons. For instance, imagine you conduct a survey that reveals a significant drop in employee engagement. While the quantitative data shows the trend, it doesn't explain why this drop is happening. So, you follow up with in-depth employee interviews to explore the factors contributing to the decline. Exploratory sequential design. The exploratory sequential design flips the order of the explanatory sequential design. Here, you start with qualitative data collection to explore a topic, and then follow up with quantitative methods to test and validate those initial insights. This design is ideal when you're entering a research area where little is known, or when you need to develop a framework or theory that can later be tested. For example, if you're launching a new product and want to understand potential customer needs and preferences, you might begin with focus groups or interviews, helping you identify key themes and variables. Once you have a clearer picture, you can design a quantitative survey to test these themes on a larger scale to ensure that your findings are broadly applicable to your audience. Mixed methods research in action. Let's take a look at how mixed methods research can be applied in the real world. A fintech company is working to design a user-friendly mobile banking app that enhances its customer experience for both tech-savvy users and people who may be less familiar with digital banking while meeting stringent regulatory requirements. To achieve this, and create a mobile banking app that's both user-centered and well-grounded in data, the company employs a mixed method approach, leveraging quantitative and qualitative methods across several phases. Phase 1. Foundational research. To start, the company conducts in-depth interviews with potential users to uncover their needs, challenges, and preferences, and shape the initial direction of the app. Alongside this, a quantitative market analysis is performed to understand broader trends and competitor offerings. The combination of these methods gives the company a well-rounded view of both user expectations and its market landscape. The company uses this information to come up with a detailed concept for their digital banking app. Phase 2. Concept testing. Next, the company tests its initial app concepts. It deploys focus groups to gather qualitative feedback, helping the team refine ideas based on user reactions. To validate these insights, a concept testing survey is conducted with a larger user base, helping the team understand which concepts are most appealing. Phase 3. Prototyping and usability testing. As the app design progresses to the prototyping stage, the fintech company uses unmoderated user testing to see how users interact with the prototype. This feedback reveals usability issues and helps refine the design. At the same time, usability metrics, such as task success rates and time on task, are tracked to quantitatively measure the app's performance. This process is iterative. They revise the prototypes based on feedback and test again to make sure the changes improve users' experiences with the app. Phase 4. Launch and initial monitoring. At the app's launch, the company closely monitors user interactions through usage analytics, providing quantitative insights into how the app is being used and where that usage leads to frustration like rage clicks. To complement this data, user feedback sessions gather qualitative insights directly from users to better understand the cause of the frustration. This combination allows the company to quickly identify and address any issues, ensuring a smooth user experience from the start. Phase 5. Continuous improvement. Post-launch, the company moves into the continuous improvement phase to ensure that the app evolves with user needs and stays competitive in the market. Digital customer satisfaction and NPS surveys are regularly used to collect quantitative data on user satisfaction and loyalty. Alongside these efforts, the company engages with users in online communities to gather qualitative feedback on their experiences and suggestions. How to conduct effective mixed methods research. Great mixed methods research requires careful planning and execution at every stage. By following a structured approach, you can ensure that your research delivers comprehensive, actionable insights. Here are the 3 main areas to get right. Defining research questions. The first step in any research project is defining clear and focused research questions. In mixed methods research, it's vital that you work around research questions that can be answered using both qualitative and quantitative methods. Start by considering what you want to learn and how each method can contribute to answering your questions. For instance, you might use quantitative methods to measure the extent of a problem and qualitative methods to explore the underlying causes. Choosing the right design. Once your research questions are defined, the next step is choosing the right mixed methods design. Whether you opt for a convergent parallel design, an explanatory sequential design, or an exploratory sequential design really depends on your specific research goals. Here, think about how you want to integrate the qualitative and quantitative data. Do you want to collect them simultaneously or sequentially? Which method will take precedence? Integrating and interpreting data. The true power of mixed methods research lies in the integration and interpretation of your data. After you've collected your data, the challenge is to bring it all together in a meaningful way. Look for points of convergence where the data supports the same conclusions, as well as areas where the results diverge. The use of a single platform can make a big difference during this phase, especially one that offers data integration and analysis. By having all your data in one place, you can compare and contrast findings with far greater ease, leading to richer interpretations and more robust conclusions a lot faster. This topic explored data storage and management methods and tools, beginning with the next level of data analytics tools and processes using the cloud-based Google Cloud Platform database tools and services. Next, we examined advanced data analytics methods and tools provided by cloud-based tools like Databricks. Finally, we explored the use of mixed methods research and the use of qualitative and quantitative data for business data analytics.